So last Thursday, you had this question to answer. I'm going to go through this answer. A lot of you had some issues with solving this problem. So I'm just going to go through it. So the first one says, or the first part of it says, a ball of mass 1 kilogram rolls down a hill that is 20 meters high and it's on Earth. Well, how do we figure out the potential energy that will have, gravitational potential energy, when it's at the top of the hill? Well, we know that the gravitational potential energy equals the mass that the rock has, the gravity on whatever planet it's on, and the height that it happens to be up the hill. Okay, so all those three are the variables that will determine how much energy that object will have. And we change any of them and it will get more or less energy. So what's the mass of the rock? Well, that's 1 kilogram. And it happens to be on Earth, so it's going to have an acceleration or a gravity on Earth of 10 meters per second every second. And it's also 20 meters up, and so that's 20 meters. And if I multiply those together, I will get 200. And you can see that the units would be kilograms meters squared per second squared. All right, if you figure out those units, that happens to be a Newton meter, otherwise known as a joule. All right, so we got 200 joules for that object. Now, it says in the next part of this question, there's friction on the hill and the ball warms up as it rolls down the hill. Half of the potential energy that the ball had at the top of the hill becomes thermal energy. How many joules of potential energy become thermal energy? Well, that's a pretty simple question. We had 200 joules and half of it turns to thermal energy. The rock warms up, so that's going to be 100 joules. And so I'm just going to make that black, and 100 joules. No work really necessary for that one. How much kinetic energy then is stored in the ball at the bottom of the hill? Well, at the top of the hill, it had 200 joules. It's not getting any energy from anywhere else. Okay, we're not adding energy to it someplace else. Nobody came with a hair dryer and heated up the rock to add energy to it. So the only energy is coming from this potential energy and being stored now as thermal energy and kinetic energy. Well, if it's 100 joules of thermal energy, then the remainder of that energy becomes kinetic energy by the time it gets to the bottom of the hill when there is zero height. Okay, at zero height, this whole equation is zero for potential energy, which means that it all must be in kinetic energy and thermal energy. So that would be 100 joules, again, left. So I'm going to go ahead here and write 100 joules of kinetic energy. All right, finally, what is the velocity of the ball at the bottom of the hill? Well, how are we going to figure that out? Well, we know that kinetic energy is 1/2 mv squared. Ke equals 1/2 mass times velocity squared. All right, and so if you're going to be able to convert that, then we'll need to rearrange that, all right, and we'll need to put in some numbers. So I'm going to put in 100 joules, and I know with looking at this right here, that half, I'm going to have to divide both sides by half, and I'm going to have to divide both sides by the m. Now, dividing both sides by half is the same as multiplying by 2. So I'm putting that 2 right here, right? And then I need to divide both of those by the m. But if I look way at the top, the mass of this rock was only 1 kilogram. So I'm going to divide by 1, divided by 1 kilogram. All right, and that's going to equal my v squared. Okay, so if that equals v squared, I need to multiply those out and I need to take the square root. Okay, so to solve this, 100 joules times 2 is going to be 200. All right, then I need to take the square root of that whole thing, that whole 200 here, and that is going to give me actually 14. And if you take the square root of 200, that's 14. So 14 meters per second is the velocity at the bottom of the hill.